Let us start with some review of Fourier Law of heat conduction in solid. Heat is a form of energy and is also capable of flowing through space. Heat flows from the part of higher temperature to the part with lower temperature, a situation similar to water flow from higher elevation to lower elevation. Heat flows in solid by conduction. Since heat flows, thus there is a definite relationship between heat flow Q and the temperature difference delta T in the solid. Relating Q and delta T is what the Fourier law of heat conduction is all about. Next, let's take a look at how the derivation of Fourier law of heat conduction is done. Let's take an example of a solid slab. With the left surface at temperature TA and the right surface at temperature TB, heat will flow from the left to the right surface if TA is higher than TB. So by observation, we can formulate the total amount of heat flow Q through the thickness of the slab as this equation, where A is equals to the area of which heat flows, T is the time allowing heat flow, and D the distance of heat flow. Replacing the directly proportional sign in the above expression by an equal sign and a constant K leads to this expression. The constant K in the equation is called the thermal conductivity. The amount of total heat flow in a solid as expressed in this equation is useful, but makes less engineering sense without specifying the area and the time in the heat transfer process. Consequently, the heat flux Q, the sense of intensity of heat conduction, is used more frequently in engineering analysis. From the previous equation, we may define heat flux as this equation. We realize that the newer equation, that is the heat flux equation, is derived from a situation of heat flow through a thickness of a slab with distinct temperature at both surfaces. In a situation, the temperature variation in the solid is continuous by the function Tx. As illustrated beside me, by following the expression in the equation of heat flux, we will have this equation. If the function Tx is a continuous varying function with respect to x, we will have the following equation from the first equation. The newer equation is the mathematical expression for the Fourier law of heat conduction in the x direction. Let's take a look of an example of question regarding Fourier law. A metal rod has a cross-sectional area of 1,200 mm square and 2 meter in length. It is thermally insulated in its circumference, with one end being in contact with the heat source supplying heat at 10 kilowatts and the other end maintained at 50 degrees. Determine the temperature distribution in the rod if the thermal conductivity of the rod material is K equals to 100 kilowatt per meter degree Celsius. To solve this, you can use the following method. The total heat flow Q per unit time in the rod is given by the source of heat at the left end, that is 10 kilowatt. Because heat flux is Q equals to Q over AT, we can express it as Q over T equals to QA equals to 10 kilowatt. But the Fourier law of heat conduction requires this equation. We thus have the equation of heat flux, that is Q equals to QA equals to negative K A dTx over dx. We can express dTx over dx as negative Q over Ka. We can now calculate the value of dTx over dx. Since this is an expression in the first order differential equation, we can now get the solution of Tx by integrating the equation. If we use the condition of x equals to 2 and the temperature equals to 50 degrees, we can calculate the value of C, which leads to the complete solution of Tx equals to 216.67 minus 83.33x.
Okay, now we continue with heat flux in space. Here I want to explain some expression in 3D form. Heat flow in the direction of decreasing temperature in the solid. In solid, with temperature variation in all directions, heat will flow in all directions. So, in general, there can be three-dimensional heat flow in solid. This leads to three-dimensional formulation of heat flux. Heat flux is a vectorial quantity with R is position vector representing in X, Y and Z component. Here are some pictures of the position vector of R. The magnitude, if we want to calculate the magnitude of vector Q, we can use this formula. As you can see from the formula, the Q, X and Y, Z component, if we want to calculate each component, we can use this formula. So in general, the heat flux vector in Fourier law of heat conduction can be expressed as Q is equal to negative K in change of heat. Okay, now I want to explain some application of heat flux. Here are the picture of the tube with longitudinal fin are common use. You can see there's a cool area and hot area. The heat inside the tube will flow along the plate fin to the cool contacting plate outside. It is desirable to analyze how effective heat can flow in a cross section of the fin. Fins are also used to conduct heat from the hot side of the internal combustion engine to the outside cool air in the motorcycle. Here are the cross section of the tube with longitudinal fin with only one fin shown. As you can see, the hot temperature will flow through the cool temperature through the heat. There is another application of heat flux using through our daily life. For example, the microelectronic cooling system. It also uses the fin to cool the chip inside of the computer.
Next, I will explain about the sign of the heat flux formula. As you know, the heat flux formula is Q in bracket S equal to K dt in bracket S over dx. So we have to determine the sign of the heat flux formula. The heat can flow either in one-dimensional or in two-dimensional. So for one-dimensional heat flow, the heat flow will flow only in one direction, either in X direction or in Y direction. either one. So when the heat flow from higher temperature to the lower temperature, it will give the formula the negative sign. Or the heat flow, when the heat flow from low temperature to high temperature, it will give the positive sign for the formula. For two-dimensional heat flow, the heat flow can be separated into two components, with X and Y components. The next step, we have to know the sign of the upward normal. Upward normal n is a normal line pointing away from the solid surface. As you can see the figure beside me, the upward normal position is a normal line pointing away from the solid surface. So when the normal line pointing to the right of x-axis, it means the positive sign. Same goes to the upward, and in y-axis it will give positive sign, and negative sign in left side of the x-axis and upward. Downward in y-axis. Next step, we have to determine the direction of Q. Either Q along N or not. If Q will determine, Q and N determine the sign of the Fourier law. So to be clear, let's take a look at one example. As you can see, the example beside me us to determine the correct positive or negative sign of the formula of heat flux. So the first diagram above show material and heat direction at the material. So the sign of the heat flux can be determined by using this table. So let's take a look at Q1 as an example. The first step, we have to look at the upward normal, and Q1 give negative n because of the negative in x direction. So the next step, we have to determine either the Q along and is not. So as the diagram show, it clearly show that the Q is the opposite direction of N. So case 4 fix all the requirements that we discussed earlier. So Q1 will give a negative sign of heat flux. The next and the last example, we will take a look at Q4. So Q4, for upward normal for Q4, is pointing downward at the y-axis. So it will give a negative sign of N. So the second step, we have to determine the Q direction, either along the N or opposite direction of N. So as we can see, the Q is clearly along the N. So Q4 is in case 3 that will give the positive sign of heat flux.
Hello everyone. Okay, we are going to look into example 3.8 where the heat flux, where we can see the heat spreader in a triangle on the heat source, of IC. So basically, it's given T is equal to 100 plus 5x y squared minus 3x squared y. Okay, in degree C, and the thermal conductivity is K is equal to 0.021. And if we see the heat spreader, the height of the heat spreader is 4 cm and width is 2 cm. And basically the highest point of the heat spreader is A, and is following the anti-clockwise system B and C. And to solve this equation, we need to set the coordinate system and identify the outwards of the heat flux. Okay, first, we draw the heat spreader, label it A, B, C, and basically the direction is perpendicularly, where you can see at surface AB is negative nx at the surface of QAD, and at the surface of AC is QAC magnitude of n, and at BC is with contact with the IC, which is the hot heat source. The direction is negative ny. Okay, so now we are going to look in A, where heat flux across surface BC. So the direction of heat flow is known, and negative Vn, the sign of negative n, is equal to case 3 or 4, and QBC is not along n. That's it, it will go to case 4 with negative sign. So with the formula given, QBC is equal to negative K delta T x and y over delta y. Okay, I'm sorry. QBC is equal to negative K delta T x and y over delta y, and is equal also where we know the K is the constant and the T, so we can substitute all the value, so it will become negative 0.021 multiplied by delta in bracket 100 plus 5x y squared minus 3x squared y close bracket over delta y. And when we substitute y is 0, and we will get 0.063x squared, the answer for heat flux across surface BC. And for heat flux across surface AB, we need to verify the direction of the heat flow across the surface first, and we need to check the temperature at two terminal points of the edge AB. Look at point B, where we know x and y is equal to 0. The corresponding temperature is, when we substitute the value of 0, x is to 0 and y is to 0 into the equation, we will get 100 degree bigger than 20 degree, which is 20 degree is the ambient temperature. So the same temperature at terminal A, and so heat flow from the spreader to the surrounding. And we can see from the diagram, the triangle diagram, QAB, where the heat flow to the surrounding with negative nx, So case 3 in Fourier Law, thus we have QAB is equal to K delta T x and y over delta x. When we substitute the value of K and T, we will get 0.021 delta bracket 100 plus 5x y squared minus 3x squared y, close the bracket, over delta x. And when we substitute the value of x is equal to 0, we will get 0.105, the answer for heat flux across surface AB. Okay, the final part is heat flux across surface AC. It's a bit tricky here because AC is an inclined surface. So we have the situation as illustrated on the screen. So using the same technique as in case B, we may find the temperature at both terminal A and C to be 100 degree, which is greater than 20 degree, and we know that 20 degree is the ambient temperature, so heat leaves the surface AC to the ambient. You can see the diagram on the screen where we can see QACY, which is going upward, and QACX, which is going on the right side. And magnitude of n, we can see the magnitude of n there. So based on the direction of the component of the heat flow and upward normal, we recognize case 1 for both QACX and QACY. Thus, we have for QACX is equal to negative K delta T x and y over delta x, when the substitute value of x is equal to 1 and y is equal to 2 is equal to, we can get negative 0.021 bracket 5y squared minus 6xy, and once we substitute the value of x and y, we'll get the answer negative 0.168. For QACY, same, just follow the step above, the previous step, and we just substitute the value x is equal to 1 and y is equal to into the equation of negative 0.021 bracket 10xy minus q 3x squared. So once we have substituted all the values, we can get negative 0.357. Yeah, the answer is right. So once we have the x and y component, to get the QAC, so using the same method as the magnitude, we just square both of them, both of the component, and square root the answer. So we'll get 0.3945 for the answer. That's it. Thank you.